Okay, let me guess. You are tired of seeing questions about series asking you, this one converge, this one diverge, and you have no idea how to start it?
Exactly.
So, you're in the right video. Welcome to the Limits of Math. My name is Belmiro Gallo, and today I'm going to be talking about three things: the divergence test, a couple of examples, and why the converse of this theorem is not true. Yeah, so let me connect here my iPad so I'm going to show you better. The divergence test says if the limit when n approaches to positive infinity of a n does not exist, or if the limit of a n when n approaches to positive infinity is different than 0, any value different than 0, then the series of a n is divergent. Okay, let's prove this test by contrapositive. Contrapositive is a rule of inference used in proofs. So you should know that if P implies Q is equivalent to not Q implies not P. Let me write here. In my case, Q is going to be the series AN is divergent. So what would be not Q? Not Q, it means not divergent. Not divergent means my series is convergent. Okay, what's my statement P? P, it is my first line here, my hypothesis. My limit does not exist, or my limit is not 0. So what would be not P? What is going to be something that exists and is not different than 0? It means equals to 0. Okay, instead of proving P implies Q, we're going to prove not Q implies not P. I know if you're familiar with logic, it's pretty simple for you, but if you're not, you should go over it. It would be very helpful. So let's assume my series is convergent, and let's call this series equals to S. So Sn, I'm gonna use that for my series from n equals to 1 to n of a n. Okay, so it means I'm adding the first n terms. Great. So as n minus 1, it means I'm adding the n minus 1 first terms. Great. So if I subtract both, what I'm going to have, yeah, it's clear here we're going to have only an, because before I had the n first terms. The second one, I have n minus 1 first terms. So I'm going to have the last term n. Great. Moreover, the series an, if you compute, it's just the limit when n goes to positive infinity of the series from 1 to n. That's the same as the limit of Sn. When n approaches to positive infinity, that's the same as the limit of Sn minus 1. So, yeah, both are going to the same place. So, when you compute the limit of the difference, it goes to 0 because both of them goes to the same spot. Okay, great, but we call the difference an, so it means my limit of an is actually 0. Okay, so far so good?
What do I do with it?
This test should be one of the first tests that you have to apply when they're asking you if a series converge or diverge. Because let's see this example. So what are you gonna do with that? Okay, I'm gonna show some examples here. So if you have the series from n equals to 1 to positive infinity of n over n plus 7, if we compute the limit, it's going to be clear the limit is actually 1, and 1 is different than 0. It means, by the theorem, the series is divergent. Great. So let's see one more example. Example B. Okay, here I'm going to have the series from n equals to 1 to positive infinity of n squared minus 1 over 4n squared plus 1. Again, let's compute the limit. That's the first thing that you have to do. I have no idea if converge, I have no idea if diverge. Let's compute the limit. Computing the limit, simplifying. Okay, I found 1 over 4. Great, that's different than 0. So the series is divergent.
Not good. Brilliant.
Okay, I have prepared now 2 other kind of examples. Let's see it. Example C. I have the series from n equals 1 to positive infinity of 1 over n. Let's compute the limit. Yeah, pretty simple, right? The limit is 0. Oh, we know this series. This series is called Harmonic series. And since the limit is 0, we can't say anything about it. Wow, okay, I have prepared here 2 different ways to show you how to compute this series. Okay, let's check the first way. We can write down the first couple of terms. And let's assuming the limit, actually, this series is going to be L, a finite number L. And then we're going to have 1 plus half plus 1/3 plus 1/4, 1/5, 1/6, and then keep going that. I know this value is going to be greater than or equal to 1 plus 1 over 2 plus 1 over 4. Yeah, so far, let's think. When I have an odd number at the bottom, I'm going to move this odd number for the following even number, for the following natural number, let's say. So I have 1/3, I'm going to move to 1/4. I have 1/5, I'm going to move to 1/6. I have 1/7, I'm going to move to 1/8. So if we proceed in that way, we're going to have 1 plus 1/2 plus 1/4 plus 1/4 plus 1/6 plus 1/6. And following that strategy, that's going to be equal to, I can add 1/4 plus 1/4. That's 2 over 4. I can add 1/6 over 1/6. That's 2 over 6. And that's the same as, I can simplify, 1 plus half plus 1/3 plus 1/4. And then we have the exactly series that we had before, but I have an extra half. Interesting, huh? And then we're going to have L is greater than or equal to half plus L. The only way to make this inequality true if L is infinity. But L, it is the result for my series. So it means my series is actually infinite. Okay, I agree with you. Maybe you don't like this kind of proof because I'm using induction, I'm hiding some other terms, I'm not writing every single term. I can give you another fair proof. But in that case, I'm going to use the integral test. I'm not going to prove it, but I'm going to state here just to remind you guys. Let's suppose a function f is continuous, positive, and decreasing on the interval 1 to infinity. And let's call an equals to my function fn. Then the series an is convergent if and only if my function f is convergent. Okay, great. How I'm going to apply that in my case of my harmonic series? I know my harmonic series is positive on the interval 1 to positive infinity. It's also decreasing on the interval 1 to positive infinity, and also continuous on the interval 1 to positive infinity. So I can apply the theorem. Applying the theorem, we're going to compute the integral of 1 over x dx. Computing that integral is the same as computing the limit when t goes to positive infinity of the integral from 1 to t of 1 over x dx. Okay, solving that limit and computing the integral, we're gonna find that that's actually equals to positive infinity because the limit when t goes to positive infinity of ln of t, it is positive infinity. It means my integral is divergent. Then the series is also divergent. Very cool, huh? Example D. I have the series from n equals 1 to positive infinity of 1 over n squared. Let's compute the limit. Okay, very simple. It's actually 0, right? Because when n approaches positive infinity of 1 over n squared, it is 0. If we use the integral test again, I can check 1 over n squared is positive on the interval 1 to positive infinity. It's also continuous and decreasing on the interval 1 to positive infinity. So if we compute the integral is going to be 1, right? Yes, 1. So by the integral test, if the integral converges, then the series is also converges. So that's very cool. we realize when I compute the limit, if it is different than 0, or if it doesn't exist, I know my series is divergent. But if it is 0, if the limit is 0, I can't say anything about it. And we saw 2 examples here. 1 over n, the limit's 0, but the series is divergent. And 1 over n squared, the limit is also 0, but the series is convergent. Crazy, right? Thanks for watching this video. So give us a like, subscribe to the channel, make comments, suggestions, share to your friends, and see you soon.